Hi again, everyone. Chris Tisdell here again. In this presentation, I'm going to continue my live stream classes of mathematics. Now, in this video, I'm going to discuss a basic second order ordinary differential equation. I'm going to show you how to solve it, and let me step you through an example to discuss the situation. Okay, so we are given the following problem. We're asked to solve this equation here. Now, the dashes means derivatives, okay? So, you know, if let's say y is a function of x, and so the y dash would mean dy dx in this case. Okay, so this equation here is known as a differential equation. Like any equation, what we want to do is solve it for the unknown thing. In this case, the unknown thing is an unknown function, such that the second derivative of the function plus 3 times the first derivative minus 10 times the function all cancels out to give 0. Okay? Now, differential equations are amazing things. They help us describe and model the world around us where dynamic processes occur. Okay? Now, let's just talk about a solution method for this one. Now, believe it or not, a very fast way of solving this problem doesn't actually use any calculus at all. It just uses algebra. Yes, that's right, algebra to solve differential equations that you find in calculus courses. That sounds weird, but actually it's very quick and efficient, so let me show you how it works. All right, so for this problem, we transfer the analysis to a related quadratic equation. Yes, a quadratic equation that you'd see at high school. And we call the associated characteristic, or the associated quadratic, a characteristic equation. Okay, let's just label this, say label it star. Is the following. Okay, so what we do is, you'll notice that each of these derivatives, second order derivative, first order derivative, 0th order derivative, has a coefficient, a number in front of it. We take those numbers and write them as a quadratic equation. So the 1 here would be the coefficient of the squared, okay, lambda squared. The positive 3 would be the coefficient of the lambda, and the negative 10 would just be negative 10 times lambda to the 0, which is just negative 10. Okay, so the 1 goes there. The double prime goes to like a power 2, if you like. The prime here goes to a power 1, and the 0th derivative goes to power 0. All right. Now, again, like any sort of quadratic equation, we want to solve this for the unknown value lambda. Okay, so you can solve this a variety of ways. You can use the quadratic formula, you can factorize. In this particular example, we can factorize. We want two numbers that multiply to give negative 10 and add to give positive 3. So 5 and negative 2 will give those the factorization. Okay, so lambda, say, plus 5 and lambda minus 2 are going to be your factors. Okay, so we know that if the product of two things is 0, then this is 0 or this is 0. So lambda will equal negative 5 or 2. Okay. Now, if you haven't seen these problems before, you're probably thinking, come on, Chris, this is a differential equation problem. Why are you showing me quadratics and solution quadratic equations? Well, believe it or not, the style of the solutions to that quadratic equation determines the solution to the differential equation? Let me show you. Okay, so the first thing we recognize about this is that we've got two real numbers and they're not equal. Now this is important because it sort of maps out the type of solution to this original DE. Okay, so we observe, so our roots or our solutions to the quadratic are both real numbers and unequal. They're not equal to each other. Okay? Hence, and this is part of a more general idea, the solution to our original problem up here is in the following form. The solution is the following, okay? It's basically a linear, what's known as a linear combination of exponentials with these two values in the exponent. Let me show you what I mean. Okay, so we've got the solution y equals this combination of exponentials where a and b are just arbitrary constants. We don't know what they are, but they're just constants. Lambda 1 and lambda 2 are these values here. So if we write that in for the, say this lambda 1 and this lambda 2, then we've got a general solution. Okay, so let me just finish saying a and b are constants. Okay, so our solution then to our start problem at the start is here. Okay, now this will be true for any a and b. All right. Okay, so that was pretty simple, right? We actually didn't calculus there. We just used a special quadratic equation called a characteristic equation, and we built that out of the original differential equation. Let me just recap. We were given this problem, okay? The coefficients are all just real numbers, okay? This is known as a second order linear problem. The 0 on the right hand side also means it's what's known as homogeneous. To solve this basic problem, we write down a corresponding characteristic equation, okay, using the coefficients associated with the y prime and the y double prime. We look at this algebraic equation and we solve it, and we look at the style of the roots. Now, in this case, the roots were real numbers, both real numbers, and not equal to each other. And in that case, the general solution to the original problem is a combination of exponentials. Now, if we got some numbers here that were like, say, -5 and 5, where the roots were real and equal, this general solution wouldn't cut it anymore. Okay, so you need to be careful with that. Okay, and then we could write down the solution. Okay, so why does that crazy method work? It's very fast, but it doesn't really give you any insight into why it works. Well, I'm not going to explain that in detail, but I can give you a hint about how you can verify that it works. This equation can be broken down to a first order problem. Okay, so you can actually play with this 3y prime term and split it up and then break it down to two first order problems. You solve those problems independently and you get two functions like this. Okay, now a good question here is, what happens if the roots of this magical characteristic equation are real and equal, or what if they're complex? Those will be the discussions of another video. The general form of solution will be slightly different. I hope you enjoyed this presentation. I hope you found it useful. Please join me again for more live streams. If you have any comments, I'd love to read them or hear them. You can put them in the comments section below. Thanks again, everyone. See you later. Bye.